Welcome to this explainer. Okay, today we are taking the sometimes intense math of chemical kinetics and distilling it down into a highly structured, board-oriented masterclass. So, whether you're gearing up for exams or you just really want to master the true speed limit of chemical reactions, well, you're in exactly the right place. Let's get right to it. Think about the physical world for a second. Thermodynamics actually says that diamonds will eventually turn to graphite. But the rate of that change, it's so imperceptibly slow, we literally say diamonds are forever. Now, contrast that with the leftovers spoiling in your fridge. Why is there such a massive difference in time? That question is exactly what we're tackling today. To get you fully prepped and confident, here is our roadmap. We'll be moving through the speed of chemistry, average versus instantaneous rates, rate law and order, reaction molecularity, integrated rate equations, and wrapping up with the half-life of reactions.
All right, let's jump straight into section 1, the speed of chemistry.
So, thermodynamics is fantastic for telling us if a reaction is actually feasible. But, it doesn't tell us a single thing about how fast it's going to happen. That is where chemical kinetics comes in. It's the branch of chemistry focused entirely on speed, the literal time it takes for a reaction to reach equilibrium. Moving right along to section 2, average versus instantaneous rates. Let's see how chemists actually measure this stuff.
Think about calculating your speed on a long road trip. You take the total distance and divide by time, right? Well, chemists do the exact same thing to find the average rate. We look at the dropping concentration of a reactant over time intervals. For instance, with butyl chloride hydrolysis, you can see the concentration steadily dropping from 0.1 moles per liter down to 0.0741 over 150 seconds. But here's the catch. Because a reaction naturally slows down as the reactants get used up, we have to distinguish between two types of rates. The average rate is great for a long period, delta T. But for exact precision, we use the instantaneous rate. That's measured at a specific, infinitesimally small moment when the time interval, dt, approaches zero. It's basically the difference between your average trip speed and glancing down at your speedometer at one exact second. Okay, section 3, rate law and order. The absolutely crucial thing to remember here is that our rate law, which relates the reaction speed to the molar concentration of the reactants, must be determined experimentally. You literally cannot just look at a balanced chemical equation and guess the exponents. The powers in the rate formula might match the stoichiometric coefficients, but they also might not. And that brings us to a massive, highly tested board exam concept, reaction order. When you add up those purely experimental exponents, the x and y from your rate law, you get the overall order of the reaction. And get this, that order can be 0, it can be a whole number, or it can even be a fraction. Let's move into section 4, reaction molecularity. We're talking about the actual physical mechanics here. For an elementary step to happen, the reacting species, whether they're atoms, ions, or molecules, they have to physically collide at the exact same time. Depending on how many are crashing together, we get unimolecular, bimolecular, or termolecular reactions. Now this right here is a classic board question. What is the difference between order and molecularity? Well, remember, order is an experimental observation. That can actually be 0 or a fraction. But molecularity, that describes physical, real-world collisions. You can't have 0 molecules colliding, and you certainly can't have half a molecule colliding. So molecularity absolutely must be a whole integer. Onward to section 5, integrated rate equations. We're going to take those differential rate laws and integrate them to track exact concentrations over time. Let's walk through the zero-order derivation, so you are totally unfazed on exam day. We start with the rate equation. Negative dr over dt equals k. Rearrange it, integrate it, and apply your initial condition. Boom. Final equation. Concentration of R equals negative kt plus the initial concentration of R. What's super cool about this is how beautifully it graphs. That final equation is basically the classic straight line formula you already know, y equals mx plus c. So if you plot concentration against time for a zero-order reaction, you get this perfect straight line where the slope is precisely negative k. Now, if you run that exact same integration process for a first-order reaction, where the rate depends on concentration to the first power, you get a vital twist. Integrating gives us the natural log of r equals negative kt plus the natural log of initial r. This specific logarithmic relationship is absolutely foundational for almost any chemical time calculation you're going to do.
Almost there. Section 6, the half-life of reactions.
We're asking a very specific, practical question now. How long does it take for exactly half of our reactant to just disappear? That's half-life. It's critical for everything from pharmacology to dating ancient artifacts, and the mathematical formula for it changes completely depending on the reaction's order. Pay close attention to this vital difference. A zero-order half-life is directly proportional to the initial concentration of the reactant. But look at the first-order half-life. It is completely independent of how much material you started with. In fact, for a first-order reaction, the half-life is always going to be this magic constant number, 0.693 divided by the rate constant K. It doesn't matter if you start with a ton of a chemical or just a tiny microgram, the time it takes for half of it to react remains exactly the same. Okay, mental screenshot time. These are the 4 essential formulas you need to lock down for zero and first order reactions, the integrated rate equations and their half-lives. If you have these memorized, you are going to absolutely crush almost any kinetics problem on your board exams. To wrap up this explainer, I want to leave you with a final thought. By mastering these kinetics formulas and understanding rate laws, aren't we essentially learning the exact code to pause, accelerate, or completely rewrite the speed limit of the universe itself? Think about that the next time you see a slowly rusting car or look at a diamond ring. Thanks for hanging out with me for this masterclass.